In today's topic video, we're going to be talking about René Descartes' rule of signs. What the rule of signs does is that if you have a polynomial, it gives you a way to know how many zeros you're going to have and what types of zeros you're going to have. Now, it doesn't tell you what those zeros are, but it tells you how many there are. So that can be very useful when coupled with other things. So, say we had a polynomial, p of x, equal to some number times x to the n plus some number times x to the smaller n plus blah, 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 all the way down to some number c. Well, what Descartes' rule of signs tells you is that if you go through and you count the number of sign changes, then that number will be the maximum number of positive real zeros you have, and then you would keep going down by twos until you hit 0. So here's an example. Say if I had x cubed minus x squared plus x minus 1. If I look at this and count my number of sign changes, I go from positive to negative here, so that's one sign change. I go from negative to positive here, so that's another one. And I go from positive to negative, so that's yet another one. So for the positive zeros, we have either 3 or 1. How did I get 1? Well, you start at your number that you counted, which was 3 sign changes here, and then you go down by 2s. If I went down by 2 again, I'd be at negative 1, and since we're talking about the number of zeros, it wouldn't make sense to say I have negative 1 of them. It's like having negative 1 coins or something. So that is the number of the possible numbers for how many positive real roots this has. How do you figure out the possible number of negative real roots? Well, what you do is you take your original function and you plug in negative x everywhere you see an x, and then that new equation, you count the number of sign changes again. So as an example, if I plugged in negative x to this function right here, so f of negative x, well, negative x cubed would become negative x cubed. Whenever you raise a negative to an odd power, it stays negative. And then I subtract a negative squared. So the negative squared becomes positive, but I'm still subtracting it, so minus x squared. And then plus a negative x squared becomes negative x, and then minus 1. So what's interesting here is if you go through and you count the number of sign changes, there aren't any. It's just negative, 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 negative. The sign never changed, so the possible number of negative roots here is 0. If it had been any number more, like if I had so happened to count 5 sign changes, which I couldn't count 5 sign changes here because there's only 4 terms, but if I went through and I counted like on some other polynomial, when I did this, I had plus, minus, plus, minus, plus, minus, and I went through and I counted 5 sign changes, then I would say there's either 5 negative zeros or 3 negative zeros or 1 negative 0. So in general, for both of these, you count them and then you go down by 2s as long as it stays positive. So that's Descartes' rule of signs. There's one more neat little detail about this. So I've shown you that if you just take your polynomial and count it as is, that gives you the possible number of positive roots. Then if you plug in negative x and count the sign changes, that gives you the maximum possible number of negative roots. There's one other cool thing. You can also figure out the possible numbers of imaginary real roots, and you do that by doing n, where n is the degree of your polynomial. P was the maximum possible number of positive roots. And Q is the maximum, possible number of negative roots. Then if you want to know the number of imaginary roots, I'll just call it capital I. That's not like standard notation or anything. That's just what I'm calling it. If you want to know the number of imaginary roots, you start off, you do n minus p plus q in parentheses. And this gives you the minimum number of possible imaginary or irrational roots. Both start with I. So this is very useful. If I use this for this example, I had a degree of 3, and then minus the maximum number of possible roots was 3. The maximum number of negative roots was 0. And so I get 3 minus 3, which is 0. That's the minimum number of possible imaginary roots. And then, instead of going down by 2, you'd go up by 2. So if I go up, I could have 0 or 2 imaginary roots. I wouldn't go up to 4 because then 4 is greater than the degree of my polynomial, so that would have to be impossible. So, positive roots, count the sign changes, go down by 2 as long as it stays positive. Negative roots, plug in negative x, count the sign changes, go down as long as it stays positive by 2. And for imaginary roots, do this formula, degree of the polynomial minus the 2 maximum numbers you calculated before, and then go up on that by 2 as long as it's less than the degree, and that would be your number of imaginary roots. And that is Descartes' rule of sign.